Very good, sir.
It's a great pleasure to welcome Parameswaran here to speak to us. And sorry about the delay. We seem to always have these little glitches to begin with. He's visiting for the next 2 weeks, I think, even, or there approximately. And he's going to tell us about fluid dynamics, edge modes, and all of that.
Well,
so,
thanks for that. It's not all of that, but anyway, thank you, Tenju, and thank you for the invitation to visit here. So I'm going to talk about fluid dynamics, which, as you all know, is a very old subject. So one might wonder if there is anything new to say at all after so many years of so many people working with it. But I'm hoping to convince you that there are some interesting things one can still say. Some of the things I mean, this is a topic I've been working on off and on for many years. So some of the things I say will be a little bit old, and some will be rather new. Okay, so let me say what this is all about. Do I need a microphone or anything? Oh, that's all. It's there. Okay, good. Okay, so I'm going to talk about a way to look at fluid dynamics in terms of group theory. And we all know the classic method of getting fluid dynamics. The idea is to look at point particle dynamics and then do some sort of a coarse graining. You consider several particles which are flowing or moving in some direction. And then you try to apply Newton's equations, but you try to do a coarse graining and replace the particles by an average density of particles and so on. And that's a classic way in which Lagrange derived fluid mechanics from Newton's equations, okay, going back to late 1700s. But when you think about it in modern language, we realize that we don't talk about point particles in the sense of something that follows Newton's equations. It's a point particle is a unitary irreducible representation of the component. It's the only way we know how to define what we mean by a point particle in modern language. So if that's the case, can we develop fluid dynamics from this point of view? That's basically what I'm going to talk to you about. Okay? And the advantage, of course, is that once you realize how fluid dynamics looks in terms of groups, we can generalize it to other groups, for example, things which apply to nonabelian plasmas. Nonabelian plasmas, I can discuss some spin effects, effects of quantum anomalies in fluid dynamics, things of that sort. Okay. And second question, I mean, this is of course emphasizing the point particle nature of the fluid dynamics. The constituents are point particles, and then you're generating a coarse grained description. But what if we don't start with a point particle point? We have a quantum field theory. Then you can ask, so if I start with something like an nonabelian gauge theory, can I come to this formulation in terms of groups? That is the kind of approaching it from the other side, from the field theory side. Can we do that? That would be another question that I would put in. Now, of course, the moment I say nonabelian gauge theory, there is an obvious problem that can arise. If you think of something like Engel's theory or QCD, we know that there is no gauge invariant and conserved current for color. Okay? If you want a conserved current, it's not gauge invariant. If it's gauge invariant, it doesn't necessarily conserve. So the question then is, how do we formulate flow of this color degrees of freedom of QCD in fluid dynamics language, and how do we incorporate that? These are the kind of questions that I want to talk about. Now, another motivation to think about this, a more immediate motivation comes from the work on the color glass condensate. So when you collide heavy nuclei together, like they do in Brookhaven or LIC, then of course the nucleons melt into some soup of quarks and gluons and so on. And the state that you get is essentially known as a color glass condensate. It's like a covalent plasma, but it's strongly interacting and highly dense, so it has much more of properties similar to glass than a plasma. And in the color glass, in the description of the color glass condensate, we know that for large nuclei, in the so-called radiolimited scattering, the effective theory, which has been proposed to describe it, would involve classically charged particles, say n of them, and they obey some sort of equation like this, where we have velocity square of the particles here. This is still a particle description, not quite a fluid yet. And then this log W comes from some sort of Wilson law. Of course, writing a logarithm of W up in the actual line slope is a bit awkward, but that is sort of kind of an approximate description that people have derived. And what I would like to do is to see whether we can improve on this. And in particular, because of the radial limit of the scattering, you can take the velocity of particles to be along the plus direction in the light cone vector description, replace the number of particles by some average density like so, and then this action that I showed you looks somewhat like this. Again, log W appears where W is the Wilson line. Yes?
So what parameter are you taking large in the radial limit?
So the radial limit means you're looking at scattering where the center of mass momentum is very large, but the transfer momentum is small.
So why do you call that the radial limit?
That's I guess Rajay worked on it at some point, I guess. It's the limit in which most of the old Rajay pole analysis would work. That you remember from the 60s and so on.
It's nothing to do with complex angular momentum.
I'm sorry?
It hasn't got anything to do with complex angular momentum.
No, but eventually we have Jacob-Big type analysis, the T channel, the T variable, Mandelstam T variable. What we're saying is T over S is small. Both are large, but T over S is small. And the T can be related to the angular momentum via, when you do this Jacob-Big expansion.
It is an angular momentum.
It is an angular momentum, yeah. So that's the idea. Okay. So very often this limit is referred to as the radial limit. And the argument they make is that this kind of approximation should apply in that. And it goes over to a fluid description when you get the so-called small x limit of the hadron scattering. X is a variable that is like the fraction of the momentum of a particle, of a proton, carried by one of the quarks. Okay, and if that momentum is small, that means if the proton is moving with fast speed, the momentum of the quark itself is a very small fraction. That means there are a lot of gluons there to make up the full momentum. So that allows you to go into some sort of a fluid description with the density. And that's the idea. Is that okay, Sean?
Yeah, okay, that's fine.
Okay. Now, I mentioned that there is an issue with the color degrees of freedom because we don't know how to define a color current that is conserved and gauge invariant. And if you think about it, there's a similar problem in the general theory of relativity because there we have, instead of color, you'd be talking about mass and momenta and angular momenta. And we know that there is no, if you simply look at the gravitational field with no matter, then there is no conserved and covariant energy moment tensor. That's again a well-known issue. And so the question is, how do we deal with that? And there is some sort of an inspiration on how to deal with that from this work by Einstein, Infeld, and Hoffman, where they related it to experiments in the following way. In their method, masses are viewed as singularities of the gravitational field, and you simply put some tubular neighborhood around it, excise it from the manifold so you don't see the singularities. So your dynamics then lives on a manifold, which is, I'm just writing the space here, space manifold minus a bunch of spheres surrounding the mass singularities. And of course they become more lines and tubular neighborhoods when you move time.
And you're assuming that the masses are small enough that they can be treated as probes.
Essentially, right. Yeah.
They don't influence the electron charge.
Thank you, James. Yeah, that's correct. Yeah. So that is the approximation considered in this paper. So now what they do is that is, so now you have a manifold where things have been taken out. So it's a manifold with a lot of boundaries associated with these tubular neighborhoods. And now you say, okay, but other than that, I have no source for gravitational field, so I apply the vacuum Einstein equations for the rest of it. Okay? So if you then write down the vacuum Einstein equations, but on a manifold with these tubular neighborhoods excised, there are boundary conditions you have to put on these on the surface of these regions. And what they show is that the vacuum Einstein equations that give you equations of motion for the masses, including gravitational interactions between the point masses. This sounds like a fairly a formalistic question, but it turns out to be extremely practical. These equations derived by Einstein, Infeld, and Hoffman actually have been used for astrophysics calculations involving rotating, orbiting stars and stuff like that. So it's really quite nice. So that is sort of the inspiration that I'm going to use to understand what happens in the pH table. Okay, so what are we going to do? I'm going to talk a little bit about surface states, how they define the particle excitations, and use an actual formulation. But since there are many things involved, so let me just give you a list of things I hope to talk about. I'm just going to talk about fluid dynamics using field theory first from the particle point of view. Then I will talk about the edge states in the field theory point of view. And then I will talk about some applications, talk about color glass condensate again, I'll talk about anomalies in fluid dynamics, spin flow features. There is a commutator anomaly in superfluids, I will talk about it, and something else which I'll refer to as peripheral gravity. So those are some of the topics to which this group theory approach can be applied that gives you some insight into the physics. Okay, so let's talk about what we are going to do. Okay, so what we need is a unitary irreducible representation of a G group, Poincare group if you simply want to talk about relativistic particles, but it may be a larger group if you include other charge degrees of freedom, like QCD. Okay, so if you want a single particle, we ask the question: is there an action which gives exactly one and only one unitary irreducible representation in the quantum theory? Okay, so we know that the idea of a point particle as a representation of the Poincare group is a quantum idea, but nevertheless you can ask: is there a classical antecedent to that, an action that I can write which upon quantization gives me this representation? And of course, such an action is known for any group. You can write this action. If U is an element of the group, you take a time derivative if you like. U inverse U dot. H's are the diagonal or the Cartan elements of the algebra of the group. And W's are set numbers, and this is simply the action that you can write. Okay, this is the simplest action you can write down. It's invariant under reparameterization of time. It's a, if you like, a topological sort of action. And say U is an element of the group in some representation, doesn't matter which one, that's just to define the trace. And W's are set numbers. Now, if you quantize this action, you will get a Hilbert space which carries exactly one unitary irreducible representation. Okay? Nothing, just one. And the numbers W will select the final representation of interest. In fact, it will correspond to the highest weight of the representation. Okay? So, and of course, if you analyze this action in a little more detail, you will see that there are quantization conditions for consistency when you translate U on the right side by various elements of the group. There are some consistency conditions that emerge in the quantum theory, which will put quantization conditions on the W, and those are exactly the correct conditions to define the highest weight of a unitary representation. Okay, so that's a nice action. This is not particularly new result. It goes back to the work of Burrell, Weil, and Bott in the 1950s, taken over and generalized to include geometric quantization by Kostam, Sulio, Kirillov, and others. And then on the physics side, Wong and Balchandran introduced this action to analyze motion of colored charged particles and so on. Okay? So that's an action that we know. And once we have this action, we can immediately do the same old Lagrange trick of taking a whole bunch of particles instead of one. We put a W sub alpha, alpha labels of particles, and then instead of summation over alpha, following Lagrange, we replace it by integration. Now recall, the way Lagrange did was to say that if I start at a given time, a time slice, I have a bunch of particle positions, and they move over to some new time slice at a later time. The particles are connected by trajectories, so you can view this as a diffeomorphism of your initial data into this new time slice. Okay, so and then when you have large number of them, almost instead of calling the particles 1, 2, 3, etc., you can simply label them by your initial positions for the particles, and therefore summation over particles translates eventually to an integration over the initial positions, and with some density, whatever the density is, and then of course here is the action. So I can combine it in this fashion, do a change of variables, because this can be related to the coordinate x by diffeomorphism. Okay, x is the coordinates that we use on the time slice of interest, so you can convert it into this. Okay.
Can I interrupt, please?
I'm sorry?
I can remark.
Okay, go ahead, Bob, please.
Along with Gianni Landi, when he was visiting Syracuse, I remember that we wrote this action and tried to quantize it. And we proceeded in some way, but we got into trouble somewhere. I don't remember. Okay? We tried to see whether it will give rise to some continuum theory, and we got into trouble. But I do remember that there was this paper with Gianni, and it is published somewhere. I don't know. Just a remark.
Which action precisely?
Sorry?
Which action precisely?
I don't hear you very well. Sorry?
Which
action did you try to quantize? The point particle action or the
No.
fluid action?
Yes. See, we like you did. Suppose, so we got this S. Okay. The S you are writing, and we tried to quantize it. And when we tried to quantize it, we got into trouble.
Yeah, actually,
I don't remember what the trouble was, but we got into trouble.
I can show you the quantum commutation rules for this. I don't know if I have it on the slides, but I have quantized it, and it is fairly straightforward to do that. I don't see any obstruction to doing that, actually.
Okay, you might have solved our problem. I don't know. Maybe.
I have quantized the continuum.
Yeah, you can have a look and see what happens. Okay.
I will do that. Anyway, I don't know this paper, but I'll look at it. Thanks. So here is where we are. And so if I now take this and add it in some kind of Hamiltonian to it, this would be the full action. Because this is just talking about the representation of the particles and so on. It hasn't really talked about the dynamics. So I have to add a Hamiltonian to that. And then this would be the action. But of course, I can transfer some terms from H back in here and write it in a more covariant way. So I will get a current, then this will be the derivative of u with respect to x mean multiplied by a current. The time component of that will be this, but I can put in the space component as well, and f would be some invariant function now rather than Hamiltonian, and it could be made of invariant currents, the square of the current. Notice that I need as many currents as the rank of the group because H's are elements of the cotton cluster. Okay? So that is how many currents I would need to describe the delta. So this action is something that we constructed, Roman, myself, and others quite some time back. But I will now talk about some of the results we can do.
You're not taking the Yang-Mills action?
No, not yet. This is just the fluid part. I'm going to bring in the Yang-Mills action a little later.
Okay, this is just
just for the fluid
particles themselves.
Just for the particles themselves. Okay. Okay. So now let me mention Let's go back to ordinary fluid dynamics and ask, how does this connect to ordinary fluid dynamics? And it has been known for a long time that fluid dynamics can be described by a Poisson bracket system, where the densities and the velocities obey these Poisson brackets, as I have described. Okay? And the Hamiltonian is given. So this Poisson bracket structure is equivalent to saying that for any two functionals of V and rho, the Poisson bracket can be written in this fashion. This last equation has the same content as these three equations. So we know that it's a Poisson bracket system, and this has been known for a very long time, over a century. But what is the problem with quantizing it? Writing an action for it. The problem is the so-called helicity, which is like a Chern-Simons term made out of the velocity fields of the fluid. And the problem with this object, which is called helicity, is that it Poisson commutes with all the observers. Which means that if you think of it in terms of, in our language of quantizing, C should be superselect. You have to fix C. And put another way, this means that if you simply write down the Poisson brackets, as I showed you in the previous slide, the right hand side, normally if I have fundamental Poisson brackets as commuting to K inverse would go into the action. But the problem here is that C commutes with everything, so K is not inverse. Okay? So that was the issue in constructing an action for fluid dynamics, starting, even though we knew that it could be described as a Poisson bracket system. So surprisingly, an action for fluid dynamics, just ordinary flow of water in a ditch. You didn't have a Lagrangian for it for centuries. It was only in the 1950s that people managed to write down a Lagrangian. Okay? It's quite astonishing. Okay, so how do we do that? We had to fix the value of C, and once it is fixed, then we had to find a way to. Yeah.
What is the difference of the
I'm sorry?
I forget what is the difference of the
Oh, what?
okay.
Oh, any function of velocity and density, any observer if you like. Anything would commute with C simply because of the way C is like a zero mode of this object here. Okay? That's basically what's happening. Okay, so I can't invert. That's the issue. So in a fixed value C.
Sorry, does that include viscosity or not?
No, this is ideal fluid. No viscosity yet. Okay. Once I have viscosity, it's much harder to describe it as a Hamiltonian system, obviously, because it's a dissipative system. So I'm just going to look at the ideal fluid now. Okay.
Isn't the system? Sorry, isn't this system have?
I'm sorry.
Does this system have volume preserving diffuse as symmetries as leaving the action invariant?
No, because I have a density, so it's not volume preserving diffeomorphisms are not. Unless you fix the density, there is no reason why that should be symmetric.
What I remember is there was also some work by Regge and Rossetti on helium-4. And they were getting, I don't remember, these are old papers. They were getting volume preserving diffuse, okay? And they were using research of Arnold to quantize, to find the unitary representations. This is what I remember. Okay? But
So there is a method, Arnold has a way of looking at fluid dynamics in terms of the diffeomorphism group, and volume preserving diffeomorphisms would enter there as well. And there is, in particularly in two-dimensional fluid dynamics, there's essentially you can pretty much formulate it entirely in terms of diffeomorphisms. But my take here is a little bit different. So diffeomorphisms from my point of view is more like doing general relativity in a diffeomorphism invariant way. But we know GR also has a local Lorentz invariant formulation using the tangent frames. Somewhat analogous to that, I want to look at the symmetric groups rather than the diffeomorphisms here. That's what I'm doing.
okay.
Okay, so once we fix C, then what is left over, the velocity is consistent with preserving C, can be parameterized in the so-called Flex parameterization in terms of three parameters here, theta, alpha, and beta. And then, of course, you can write down an action for it. Okay, so just for the theta alpha, the change in C actually, the change in C will come out to be 0. And once we realize that, we can write down an action for this, constructed by Lin in 1950s, generalize it like so, to again move some of these velocities as some auxiliary currents over here, write it in this fashion, then this is the fluid dynamics action. That's just ordinary fluid dynamics now, formulated in action terms, and cover the two related, since I'm going very slowly. Let me just say that if you take a group element like a CP group element, take diagonal element, take T inverse Tg, you can write it exactly in the Clefts parameterization. So the Clefts parameterization can also be viewed as having a group theoretic origin. And once you do that, you realize that this, what I just showed you here, by fixing the helicity and writing an action, like on this slide, is the last line of that slide for the action, can be written in terms of what I had before, like over here. Okay, so there is so the group theory way of understanding we can now recover also in this language. Okay, so now I'm going to tell you a little bit about edge states before I go on to applications. Is that clear? Okay. All right. So let's look at a gauge theory. And of course, we know that in the gauge theory there are constraints on how the Gauss law is implemented. Here is the Gauss's law that we normally write in the nonabelian gauge theory. And the consistent action of this G naught on all the waveform flows of the theory would require that theta should go to 0 on all the boundaries of the spatial time slice. On the other, so once we agree that this is Gauss law is implemented with theta going to 0 on the boundaries, we can consider this operator G of psi, which is almost the same as this, but notice that the derivative goes on the test parameter, test function here. So it looks like the Gauss law, but there is a vector surface tension law. Okay? So psi is not necessarily 0 on the boundaries. The important thing about the second operator is that it generates physical states because G naught and G psi, you can see that they commute weakly on any function for which G naught psi is 0. Because I can move the G naught to the right side, the commutator of the two gives me something again in G naught, which means the parameter on the side goes to 0 on the boundary. So this is still a physical state. So that means the action of G psi in the state still obeys Gauss's law, as it should for any physical state here. And these generate, therefore, physical excitations of the theory, or physical degrees of freedom, which we call the edge states of the theory. Okay? That's how they would appear in a gauge theory. Notice that ultimately the psi is an element of is infinitesimally, I can think of it as an element of the group. Therefore, basically, what characterizes the edge states is the group element from the boundary to the group. Okay? That's what it will be. Okay, now let's look at the Einstein-Infeld-Huffman strategy. We assume there is some medium which is made of charged particles, maybe nonabelian degrees of freedom, whatever, and we excite small spheres around the charges. So remove these spheres from your free manifold or tubular regions going forward. By the way, this is current load with the value 1 go up. And then you look at the angular action, and you look at the variation of the action. I can write it this way. There is this, here is the variation, you have the integration by parts. Here is what would constitute the equation version. If I put delta is equal to 0, and here is the boundary. So if I have an arbitrary boundary term, I realize that the variation problem is not well defined. I need to do something about that. Okay, so I had to introduce some additional terms in the problem. Now, generally, these tubular neighborhoods, I I'm excising from the formatting mode. There could be curved lines and so on because these are eventually supposed to be whole lines of particles. But for simplicity, I'm going to do a diffeomorphism of this, straightening out all of these lines, which I can do because it's a local diffeomorphism. I can locally change each one of them. Okay, so I straighten them out. So that's a coordinate transformation, just to make things simple. And once I have that, the boundary terms. So this equation would return the boundary term looks like this, but size are the new coordinates in this whole lines have been straightened out. And I look at the surface terms. There is an electric field term here, and there's a magnetic field term here. This term will go to 0 if I start shrinking the size of these regions to be small. Now I realize, looking at this, that I can eliminate this term if I add an extra boundary action. What is the boundary action I need to add? I need to add something that cancels this. So locally, let us just diagonalize this electric field, that's all, and make the same transformation for the magnetic components. Then this object I can cancel by writing in surface term like this. Okay? So this delta A, the 0th direction will essentially give me that, will be the field here, and this will correspond to this. So I can cancel this surface term, and therefore the theory that gives me a well-defined dynamics would be, it's there. So the boundary term that I should add is this. I just made, this is of course delta A, I have to make the whole thing gauge in value. So this is the extra, this extra term on the add. And this action, therefore, if I add as a boundary term to the angles action, now I have a very well-defined variation problem. Okay? That's a strategy. Now, once you do that, you realize, let's look at a number of boundary regions excised. Here is what it looks like. So I have the angles action I start with. This is the surface term added to make the variation problem well-defined. And this K, because I diagonalize those electric fields using the U matrix, is just of this form, diagonal generators with some weight factors. Okay? That's a question. So this tells us that now we have an action that looks very much like the action that I showed you before for point particle dynamics. Okay? So we can now put everything together. Take this part, which was the point particle action I showed you before, but now derived from as a boundary term in the gauge theory, coming from the field theory side. And now we can do a coarse grain and write this action. Okay, so this will be the action for the edge state dynamics, but coarse grain so that these particle movements or the particles that have a high density and they flow like liquid. Okay? So this is the current associated with that. Okay? So in this way, from the gauge theory, we can also get the idea of the same kind of group theoretic description. Okay, so now what do we do with it? Well, a few things, interesting things we can do. Let me go back to this point particle action. If you do SU2, then this will be some sigma 3 matrix, some number here, and here is a parameterization for the SU2 matrix. You quantize it, this drops out because it's only sigma 3 here, so this is a surface term. It gives you a quantization condition of W, but it drops out from further consideration. This SU2 mod U1 has a complex structure, and that is what you will pick up from here. You quantize, you get coherent states. Okay? This will be a representation of SU2 in the quantum theory. So what that tells us is the following. If I write a Wilson line, there are these A's are matrices in SU2, path ordered. So I do the same trick that we normally do in path integrals. You do it in infinitesimal segments in an ordered fashion. Use a completeness relation for these coherent states, and I can transform this into a function. Okay. and the functional integral would take its form with an additional z integration. And the action that you get is exactly, again, the same action showed with cosine, ln, and so. Okay? So what that means is that now we can go back to the product loss description I mentioned. Yeah, go back, please. So remember, this was what I initially introduced as the description of charged particles in the radial limit of scattering. And so this log W, now we can give a very precise meaning to this whole term. What does it mean? It is simply that action that I showed you. Taking the logarithm of a normally taking the logarithm of a Wilson line with path ordering and so on is an awkward thing to do. But here actually we have essentially written it as a single term up in the exponent. So this goes into the path ordering directly and gives you a precise meaning for what is meant by that logarithm that you show.
But that's not quite the logarithm of W.
It's not quite the logarithm.
You certainly can put it into the path integral.
That's right. But what I'm saying is that this is what they should have put in from the beginning. Their derivation of that action with the logarithm, it's a formal derivation. They're unable to give a meaning to log W except by some expansion scheme.
Yeah, okay, so you're going to put in W to the Q alpha, your expression had a Q in it.
The Q is built in here. It goes, it is this n times sigma 3 is the charge. So the whole thing is there.
So, so this is not quite the same Wilson loop. This is Q to the Q log W in the previous one.
This whole thing.
Also, so that's equal to Q1. And Q is coming, how do I read off Q here?
So Q, if you work this out explicitly, in this SU2 case, where these are sigma A1, 2, this would be the charge density Q. Okay. All the three directions of SU2.
Okay.
Okay. So when they were doing this, if you expand the log W in some fashion, as they were expanding around W equal to 1 and then try to work it out, it becomes quite awkward. And it was not a very rigorous derivation that they were doing.
So this is a sum of Wilson loops.
This is one Wilson loop.
So I mean, I would think of one Wilson loop as a path-ordered exponential.
That's correct. That's this.
Yes, exactly.
But the point is that this is a nonabelian field. So because there is no nonabelian Stokes theorem,
yes,
what you end up doing is that this statement I'm making here is the nonabelian Stokes theorem. It's not going to be called away integrated over surface. It's going to be a functional integral that represents the whole Wilson. Okay. That's the only way to.
You now have parameterized have you parameterized your gauge field in some way in this?
No, gauge field is in here. So whatever it is.
A0. This is a mu, is this?
A mu x mu dot.
Okay.
So this is the full gauge field as I have here. Except that the color matrix here, I have written effectively. I'm able to write an abelianized version because of this.
So the integral here is an integral over the u, the z integral is
Yes,
what's remaining.
it's effectively an integral over u mod u1 with this.
This is performing your path ordering for you.
Exactly. That's the idea.
Very nice.
Okay. So the path ordering can be traded for this C number calculation.
And little n is?
Little n defines the representation in which the particle lives. That's up to you to choose.
In my Wilson loop, I would.
You would still. It goes into the choice of the matrix is here.
See, it's related to the size of that matrix. So
Exactly.
So you're just saying the size of that matrix.
Size of that matrix. In fact, n plus 1 would be the dimension of the matrix in this one if you quantize it.
N plus 1 is the dimension of the matrix. I mean,
N is like 2 times the J value of your SU2 representation.
sorry, this is particular to SU2.
This is okay.
Yeah,
It can be done for anything.
then I'm fine.
Yeah.
SU2.
You can generalize to any group.
Yeah, no, I was thinking SU1, but it's,
Yeah. So, okay, so we can do that. So we have a, I'm sorry?
You have only the parameter Z, but in bigger group.
You will have more parameters. Correct. So
this depends on which co-adjoint arbitrage you're using.
yeah. So remember, I was writing this with the diagonal generators. What we are saying is that this is basically this for SU2. But if you want another group, you'll have to put more W's and more diagonal generators. So there'll be more parameters, as many as the rank of the group characterizing the representation. Is that okay? Okay, so once we have that, we can now see the fluid generalization that will work in the case of the Carnot-Glass condensate to take some form like this. Engel's term. This came from the surface terms of the H states, but it is a co-adjoint orbital fluid description. And you could have something that depends on your currents, U, gauge fields, etc., that come from integrating out the gauge fields in a more systematic way. There could be additional terms, which I haven't focused on. But you might ask how do we determine? We'll come to that. But also I mentioned when I was talking about this initially, that you could look into the Rayleigh limit of scattering, small x physics, I can describe by this, kind of a high-point description, again for the fluid, and you again encounter the same issue with the Wilson line, but now we have a better description of fluids here. This would be the term that you have. Now, regarding the last one here, that's a much harder calculation because that requires full-scale QCD dynamics if you want to calculate it exactly. So what people have done in many of these cases is to say, let me simply take a random probability approach, that there are so many, in the small x limit of the scattering, there are so many gluons that I can do. I mean, I don't know what representation they are in, I simply do a probabilistic analysis. Okay, so these gentlemen gave a probabilistic argument for that, for the small x distribution of quarks or protons or large nuclei. In our case, it's much simpler to formulate that question because the representation, if I'm talking of a particle, the representation is simply characterized by, say, for SU2, just by this integer n. Okay. And that's a positive integer. And then, so if I think of how I am choosing that, by combining representations. Imagine you have two fundamental representations, I combine, I get a spin one, then I combine it with another spin half, I jump either up or down, and so on. You continue that, you realize that if you do it k times, the probability you end up at some value n, I can write the recursion rule for it. At k minus 1 steps, either I was at n minus 1 and jumped up with probability half, or I was at n plus 1 and jumped down by probability half, and therefore I can simply write a recursion rule like that. Okay? And I can just calculate that, because if you take the larger, you notice that, if you look at it from the discrete point of view, you see that it's like a discrete Laplacian on n. Therefore, it's not a big surprise that if I take large k, large n limit of that, I get the diffusion equation, and I find that this is the probability distribution for the possible value of the representation that you would get. Okay? So that implies that the mean square value, J value, this is just for SU2, which is like k from here.
I missed some steps.
Yeah.
Can you go back one slide?
Sure.
Just concentration lapse or something.
So I take this equation.
This one is trivial.
So now I know that the k minus 1 I can trade for K by putting a D over.
Where did this process come from? That I missed the connection of this with what you were doing earlier.
Oh, okay. So what happens is we want to estimate this.
Yes, and you're just replacing it by a random coin tossing in.
Essentially, because the idea is that in the limit that they're going to apply this, there are so many gluons around.
Yes.
So it's you're group theoretically, you're combining a lot of representations together.
Yes.
And then you ask, what is the probability that I get a particular representation? Okay, so you assume that since there are so many gluons, I can do it as a probabilistic analysis.
And you're just saying that it is simply just probability of 1/2 that I go.
Oh, for this
representation.
For this SU2 case, it is just that, because it's just one number. And if I'm at a given representation, the next set of combining it with another fundamental representation or adjoint means I'm jumping down or up.
Yes.
Right?
Okay, yeah, no, that's right.
So it's a
random
walk, basically.
Yes, it's on your integer lattice, yeah.
That's what this is. And because it's a random walk, no big surprise, it should be some sort of diffusion equation. Right? So that's basically what I'm saying. So that suggests that the J² value goes like the number of steps K, which effectively means that the action will be quadratic because the mean square fluctuation, it should mimic a Gaussian, so it is very some sort of structure like this. So if I buy that, then I can actually give you a full relativistic generalization of what these color glass condensate people have done. Okay, which is essentially this last one here. Okay. So that's the application to color glass condensates. So that gives you a generalization of previous work on color glass condensates.
Would you have to specify what MIJ is now?
Yes, that's right. So right now we don't have a way of specifying that because this is just a probability argument. But presumably those can be fixed by some scattering data. That's the hope. Now I want to talk about something else which is very interesting, which is that let's talk about anomalies. We know that quantum anomalies occur in quantum field theory in many cases, and I want to see how we can apply it and derive some physics out of it for the fluid dynamics discussion. Okay. So standard model, I have the color group. And these are the chiral symmetries of the standard model. Left and right chiral symmetries associated with the up-down and strange pulse. I'm ignoring weak interactions for now, even though you can put them in also. And we want to ask the following question. Suppose, I talked about the quantum plasma or the color glass condensate, but suppose we take this whole standard model and heat it up to very high temperature. Everything goes into fluid phase. Okay. And let's see how we can describe it. Okay. So that's sort of the idea. So we know that we should get terms, currents associated with the diagonal generators of the pattern algebra, group elements associated with the symmetric groups, left and right. So these are the terms. And there will be some function that depends on all the invariants I can form out of these J's. So it would be J square, J3 square, J8 square, things like that, maybe cross terms as well. But most importantly, there is another term we need, which is a Westerminer term. Okay, let me just answer the question. I see the question there. I believe the answer is probably yes. I don't know too much about DBA actions. I know that there has been a lot of work on that. There is a way to translate some of the brain actions into fluid dynamics. So I believe that if you do that for the DBI type action, it should ultimately end up with something like this. Would that answer the question? I don't know. Oh, okay. Okay, let me say now another thing about the Westerminer term here. Why do we need it? And what am I talking about? This is fluid dynamics. Even though I write group elements, remember these group elements are parameterizing the velocities of the various fluids and so on. Of course, I need a lot of different ones. A simple way to understand that is even going back to Poincare group, think of it. You have a mass transport possible, but also spin can be transported from place to place. But I can have a situation where spinning particles combine in a spin singlet, still having mass and moving off, which means I would have mass transport independent of spin transport. Okay? So that means I need different transport equations for each of these things, which is why you have a full-blown set of the diagonals here and corresponding group elements of the velocities. Okay? So that's sort of a physical way to think about it. Now let's talk about the visible term for a moment. I can take a few more minutes.
Oh yeah, there's no rush.
So here's an argument. Tufte had a very wonderful argument for why there should be a residual action for anomalies. And that was the following. He said, let's take the theory of standard QCD with quarks with all the chiral symmetries. And imagine for the moment you gauge the full set of chiral symmetries. We know that the chiral symmetries have anomalies. But you are going to put in a bunch of extra particles to cancel all those anomalies that the quarks plus these fermions that you put in together is a completely consistent theory, no anomalies. Okay? So for that reason, we call these guys spectators. They're not playing a role except to cancel these anomalies just for the sake of this argument. And then he said, well, now look what happens. If I confine the quarks, where the confined phase, where the quarks are replaced by mesons and baryons, I do nothing to the spectators. What happens to the anomaly? Well, the anomaly should still cancel because I have a consistent theory. So that means, since the spectators have an anomaly which was originally designed to cancel the anomaly with quarks, I should simply have a term I can construct from mesons and baryons, just using the meson-baryon fields, which will cancel the anomaly generated by the spectators. And that's called the visibility term. That's the physical way to understand why there should be a visibility. But what I can do now is to take the same argument and run it in a different direction. Instead of confining the quarks, what if I'm going into a fluid phase where the whole system is described as a fluid? So now I don't have quarks as my variables, I don't have mesons, I have fluid variables, flow velocities, charge densities, that kind of stuff. But the spectators are still hanging around, so there should be something in terms of fluids which cancels this anomaly. So there must be a fluid interpretation of the Weismann term that deals with the anomalies. Okay? So what is that term? That's basically easy to construct because we're talking here about group theory. And that's one of the reasons why group theory is useful in the fluid context. Okay? And I will show you the Weismann term. Of course, I'm not expecting you to go through all of this and figure out where everything is right. But the point is, it's too complicated. So
There'll be a half there at the bottom.
Exactly. So I'm going to just pick off some of the terms to read off some real physics out of it, okay? Because there are too many terms here to, do term by term analysis and so on. So let me talk about something called the chiral magnetic effect.
Sorry, I have a simple question.
Yeah.
Maybe you said this already. What did you mean by spectators there?
Okay, so the idea is, so we had the quarks and the gluons. They have chiral anomalies for the chiral symmetry group. And I cannot gauge the chiral symmetry because they are anomalous. So Tufte's idea was add a bunch of extra fermions and they will create an anomaly which compensates the chiral anomaly of the QCD fields, right? So now I have a completely consistent theory. Now I can do whatever I want. Now you say, what if
But they're supposed to be spectators.
They're spectators. They don't have any other.
Make them spectators?
They will remain spectators. They're not going to do anything more to the theory other than just the anomaly
They could be
cancellation.
very massive or something.
Okay. And then the quarks go into the hadronic phase of mesons and baryons. And the spectators are still there. But now, of course, the spectator anomaly of the spectators now have to be cancelled. So in terms of mesons and baryons, I must be able to write down something which reproduces exactly the same anomalies to cancel the spectator, right? So once I have made that argument, spectators can be discarded. That's the idea. Okay. Now I'm saying run the argument in a different direction towards the fluid phase rather than the confined phase. Okay, it should still work. Okay, so that's the basic idea. And now once you have so basically that means fluid dynamics should include anomalies for the area. And if you take, for example, the anomalous contribution of the electromagnetic current, it will look like this is some chiral field. If you think in Masonic language, that will be like the eta prime. But for us, it's some kind of chiral flow velocity that enters. This is the electromagnetic field. And if you write the current, the space components of the current is proportional to the magnetic field, and this is the difference of chemical potentials. Okay, in the equilibrium phase of the theory. Okay, so that what that tells you is that the anomaly generates an electric current in the direction of a magnetic field, and that's known as the chiral magnetic effect. And people hope to observe this. I don't have the slide explaining it.
We have enormous magnetic fields.
Yes. So what happens is you have this nuclei that we're colliding. Okay, and most of the time you don't get right head on. They're slightly off center. So you have this charge passing this way and another set of charges this way. It creates a current and a current with the right hand rule big magnetic field. Okay? 10 to the 17 Tesla, huge. Right? Of course, it lasts only a short time, but that's enough to equilibrate the core-gluon plasma. So you have a plasma in this magnetic field, and then, of course, eventually the things come out of this plasma, charged particles and so on. And if this is correct, you should expect more charged particles in the direction of the magnetic field compared to the opposite direction. Okay, so that's an asymmetry in the charge distribution that arises from the anomaly. That's what's called a chiral magnetic effect. Okay.
Has it actually been observed?
Okay, so if
There
you
was some excitement about it a few years ago, was it?
Yeah. So if you actually look at the data, there is an asymmetry. Okay. Now, of course, there is some concern because it's a very complicated hydrodynamic system that you have to simulate to get all the dynamics right, and so it could also be that there is other ways of explaining it. So it's not completely confirmed, but definitely there is an asymmetry observed. Whether it's only the chiral magnetic effect or something else, that's the question.
This was in the heavy nuclear collisions.
Heavy nuclear collisions, originally at Brookhaven, but now LSC also has data. Okay. So that's a real nice physical effect that arises, combining anomalies, fluid dynamics, and the group theory description of fluids, everything together. Okay. Another effect that arises related to that, this is also read off from the Wesleyan curve. The electromagnetic current also has terms proportional to the gradients of flow velocities and is symmetrized. So this is like a vorticity kind of effect, and these are of course related to some F is some enthalpy function that I quoted the depth that you saw earlier. So it doesn't matter what these are. But the point is that there is an effect that is generated by vorticity in the current. Okay? Instead of magnetic field, this vorticity, because of the epsilon, this is a curl of U, which is some sort of vorticity, and that can create similar effect. So that's known as the chiral vorticity effect. There's a chiral isospin asymmetry arises the same way, just like a chiral magnetic effect, but along the peak isospin directions. So these are all effects that could be observed in the core-gluon class. Okay. Let me see. Another interesting thing you can do, which is to go back to what I started saying. Mainly, if you look at a relativistic theory, we're supposed to simply look at the Poincare group, okay, and then come back to that here. If you quantize using the Poincare group, the same action, you have mass and spin, and you can write our equations of motion for them, and this is simplified version. Notice that this is, if you take u to be mostly time direction, this is like the time derivative. So this is the analog of the Euler equation. Okay, this is a relativistic Euler equation. and P is the pressure, which is related to that function F that I showed you before. The Hamiltonian-like function. Okay, so that is not a big surprise. This is an Euler equation. But there is a spin density because it's a relativistic system. And the spin density has its own flow, which you can write down. So there is a spin flow equation you can write down. And notice an interesting effect here that a particular combination of gradients of pressure would actually give you a spin precession. This is like a spin precession equation. And there's a spin precession that happens because of spin orbit coupling due to relativity. Okay? So which is a kind of a new effect which I don't think has been noticed before in the context of fluid dynamics. Okay. I have a couple of topics more, but I don't know how much time you want. Listen to me.
We can get there. I mean,
okay. Here is something.
You seem to only have a few more transparencies, so we'll listen.
Yeah, let me see how many.
That's okay. So don't worry.
Okay. All right. So here is something I found fascinating, which is the following thing. This is some kind of a condensed matter thing that combines the fluid mechanics that I'm talking about, my way of looking at it. It's superfluid helium, so condensed matter physics, but it also has some interesting twists regarding symmetries. Okay, so here's what happens. You look at superfluid helium in a bucket or something, you rotate it, and we know what happens. It develops a number of individual vortices all moving the same way. Okay, so I have a whole collection of vortices here. And they're all flowing in one direction, and so you call it a state of chiral flow.
This would be superfluid helium-4, I think.
Superfluid helium-4, right. So what we want to do is to analyze this by approximating these vortices themselves by another vortex fluid. Right? So the fluid itself is made of helium-4 particles. You have a fluid description. Now you have vortices. Now you say large number of vortices, so make another fluid out of it. Okay, and ask what happens. Okay, one can do that. I'm going to tell you a little bit more. The problem is effectively two-dimensional because of the vortices. You're looking at the transverse cross-section mostly. So use complex variables for the positions. And here are the equations of motion of the vortices. Okay, how they move around. If there is an overall angular velocity, that's this capital omega, that's for the whole system working together. Okay. And then here is a vortex-vortex type interaction. Okay. So positions, difference of positions with some strength of strength. This is constant. And some of all vortices. Okay. So those are the equations for a bunch of vortices interacting in just ordinary fluid dynamics.
So do you say if there is an overall angular velocity?
Yeah. So I'm going to consider a situation with not only each vortex going around like that, could be also an overall angular motion. Okay.
So they don't necessarily have to have the same angular velocity?
No, I'm going to show you the relation between the two. Yeah. Exactly. Indeed, that is the case. Okay.
Sorry, let me interrupt.
I'm sorry?
Let me interrupt, if you don't mind. This looks like vortices in a type 2 superconductor.
It's very similar. Exactly. That's correct. The only difference is that vortices in a type 2 superconductor may not move freely because it's embedded in some solid. But here it's superfluid helium, so they can move freely, and so you can think of making a suprafluid out of vortices. That's the only difference, actually.
From what I know, these type 2 superconductor, when you have these vortices, they form a crystal. They crystalline lattices. Okay?
That's right.
So,
that is, yeah.
So,
that's one limit, actually. But we are talking of a different limit because this is helium. They can freely move, so they don't necessarily form a crystal.
Okay, go on. Okay.
Okay, so it turns out that the Hamiltonian governing those equations of motion I showed you were written by Kirchhoff already in the 1880s. And he noticed a couple of things. One is that this is the overall angular velocity term. This is the Hamiltonian of the interaction between the particles. And the two coordinates, z and z bar, are Poisson conjugate to each other. So there is a Hamiltonian structure for this, which was observed by Kirchhoff and it was given by. So if you look at this, you notice that the logarithm will obviously lead to the right hand side of my equations of motion with those some brackets. So this is a nice Hamiltonian system. And one can now write down the ground state wave function of the theory for n vortices, calculate commutators or nonabelian density, all kinds of things can be done. Okay? So for Wigman did the following calculation. In the large n limit, he argued that he did an anomalous algebra for the momentum densities. Okay, so these are two of the momentum densities. Because we use complex coordinates, it's p and p dagger. This is what you normally expect, just from the diffeomorphism algebra. And here is an extra. Okay, so we have an anomalous commutator, which is a bit surprising because anomalous commutators for energy momentum components means you have a gravitational anomaly, a diffeomorphism anomaly. Okay, how could there be? Because in 3 dimensions, this is 2 in time. In 3 dimensions, there shouldn't be a diffeomorphism anomaly. So this was a kind of the puzzle that started me with this. Okay. Okay. So the question is, how do we understand this? Now, of course, I should also say that the density of the vortices is related to the overall angular velocity, but this is basically what we were asking about. There's the big omega and the vorticities are not the same. There is a difference, which is okay. So the density of the vortices. So if you think of the vortices and some density, that gives you some angular velocity, but plus something is going to give you the overall velocity, right? So that's the state. So sorry.
Just is there a constraint on gamma?
No, gamma. So gamma is the strength of each vortex. So far, there is no constraint. Okay, I took all of them. We have the same strength of all the vortices.
And where did little omega enter? I don't see it in your Hamiltonian.
It's in the Hamiltonian.
Well, that's capital omega.
Capital omega.
And you're relating.
Little omega is buried in gamma, basically.
You're relating gamma to some little omega.
Yeah. Okay. The density of the vortices and the vorticity and density are related to the gamma. Okay. So we have a relation like that, and now we can ask, okay, how do we understand this in terms of fluid dynamics? So here's what we do. We write down a fluid dynamics action, as I showed you before. So Hamiltonian, there's the action. But then you realize, thinking in the group theory language, there are many topological terms you can add to the fluid action, which again is something that people have not thought about very much in the past. Okay. There are many, I have a classification of those, but let me just focus on one of them, which is the wedge product of this little one form with omega. Okay. And this is put in to obtain the constraint that I showed you in the previous slide. Okay, if you vary A0, then this is proportional to the vorticity, so this becomes the constraint that I displayed before. Okay.
Replaced gamma by rho minus rho bar.
Right.
Gamma, I mean, the term originally looked like a van der Waals. So the logarithm of the van der Waals.
No, that's a Hamiltonian you're talking about.
Yeah, in the Hamiltonian, you've got the logarithm of van der Waals there.
That's right. But I'm simply talking about.
Oh, sorry, yeah, you're just looking at the equation.
Yeah, I'm just looking at the constraint equation. Remember, gamma is just on the top of that denominator there. That's the strength of the vortex.
Yes.
Okay. And that goes into that last equation, the constitutive relation between big omega, little omega, and the density of vortices.
Yeah.
Okay. That equation I want to derive as a constraint, so I put in an A note. And this one, if you compare this to fluid velocity, this is the vorticity, and therefore this is okay. Now, once you have that, you can go through, for example, you can do a clutch type parameterization if you want by expanding this out, like so. And then you can work out the consequences. And here is what you find. Wait, wait. Yeah. Okay, so the term I'm using is this, and once you have that topological term added, you can calculate the momentum densities and calculate directly the Poisson bracket between the two, and you find exactly the same result that we will difference. Okay, so what have we done? A good analogy for what is happening here is look at the Kac-Moody algebra. If you are dealing with fermionic currents, the Kac-Moody algebra is obtained by delicate point splitting that you carry. Okay, you calculate the commutator anomaly from point splitting, and you find the central extension that you. But at the same time, you know that there is another way to think about it, which is you write down a Weismann-Witten action, whereupon the Poisson bracket structure directly gives you the central extension. Okay. So, in a similar way, what Weigel did was the point splitting type of analysis. And what I'm presenting here in terms of the fluid action is the analog of directly getting it from the Weismann-Witten action. Okay. So that is a way to understand that. Okay. I will spend just 5 more minutes. Otherwise, I won't take too much more time. Okay. Okay. So I want to go back to gravity for a second. I mean, because we are talking about Poincare group, you like to relate it to gravity, right? And the way to do it, of course, you know, the gauge theory, whose edge states would reproduce Poincare symmetry, would be gravity. So in principle, you need to look at full-blown gravity to understand how Poincare group representations arise. But you know, if you're talking about particles in the air here moving as a fluid, and if you tell me that I need to understand all of GR before I can do anything with those, that's a bit of an overkill. Okay, there must be a simpler way to deal with that. Okay, because we know that the gravitation interactions between molecules in this room, it's negligible pretty much, right? So what do we need really? We need a theory that basically gives you the Poincare group representations of the particles we need, but we don't care about any dynamics beyond that. Okay, so you need a theory from the point of view of these tubular regions, which simply resides on the tubular regions with no interaction connecting two different tubes. So that is what I would call a peripheral gravity, because it resides on the periphery of your manifold. Okay, can we write an example of that? Well, there is one classic example, which is the Einstein gravity in two cosmic dimensions. There it is known for a long time that standard Einstein gravity can be written as the difference of two Chern-Simons terms, left and right, where A left is made of the spin connection and the fermion or the tri-binary space P, and L is related to a cosmological constant. So it's omega plus E and omega minus E for the right hand side. Take the difference of the Chern-Simons, simplified substituting these, you see Einstein action plus a cosmological constant. Okay? So that's whole story, goes back to the 80s. We know that can be done like this. Okay? So can we analyze this and see what happens? Because these are two theories which smack very much of being purely topological. Okay. So that's one thing we can try, suppose. And the answer is, you can look at the boundary terms, and they do precisely lead to the terms I showed you before. And there are two, there's a left group SO21 and a right group, because there are two Chern-Simons terms, and you get two such terms here, okay, corresponding to the left and the right piece. What that means is that if I then look at the representation theory that follows from here for these particles, Q's are various charges I can put in, then this does give me a representation of the ADS group with mass and spin given by the sum of the Q's and the difference of the Q's. Okay? Okay, so you can actually get representation. So in this case, of course, it is SO22, SO21, That's the antidecided space we're talking about. Okay, it's in lower dimensions. So then we ask, okay, with that understanding, can we do it in 4 dimensions, 3 plus 1? Well, you can construct a BF type theory where B is a 2 form. F is the standard field strength associated with some group. To be, in this case, we'll choose it to be the Poincare group. Okay? And then you notice that B has a gauge symmetry that if I shift it by D plus D by C, where C is a 1 form, then because of the Bianchi identity and that, action is invaded, you have to do derivatives. These are the gauge transformation properties. So there's a BF theory you can write down and you can quantize. Okay. It's not a big deal to quantize things like that. If you look at the bulk equation solution, you can see, I think I should have said it before. If you look at the bulk equation solution, it's just B times F. You vary B, you're going to get F equal to 0. Vary F, then D wedge B should be 0. So those are the equation solution. F equal to 0 means that the connection can be set to 0 if you like. Put that in here, you see that B is closed form. Effectively tells you there is no bulk dynamics. So it's a pure topological theory. Okay. What do? You now say, okay, now I'm going to introduce my boundaries, various tubular regions, and I'm going to look at what surface term I should add. Same kind of description as I did before for the gauge theory. And here are the surface terms. You add and you find that if I take very small spheres, then the integral of this B, there are 2 parameters correspond to momentum and spin. Okay. Actually, momentum is P naught, which means mass and spin. So the action that follows from S of B, as I displayed, you ignore the red terms because they vanish when you go to small spheres. Okay. Then that gives me exactly the kind of co-adjoint orbiter actually mentioned. The traces have to be evaluated, but I will use SO41 rather than Poincare and use gamma matrices to represent the group. Everything can be calculated. Here's the action. Okay. This is the mass transport, spin transport. U is an element of the Poincare group, and here is some coding left. Okay. So one can then work out the dynamics, and some of those things I already told you. If you do fluid dynamics, you get the spin orbit coupling and the precession of spin density due to gradients of the flow. Okay. So a number of things like that we can do. I think I have overstayed my welcome. So thank you so much for listening.
Questions? Someone else?
So I guess that the F theory for the city you can put on any kind of topology.
Yeah.
I guess it will compute some interesting invariants.
Probably yes, but I mean it's only just very recent, so I haven't looked into all the possibilities. But answer is I would imagine yes, actually. Okay. I mean we haven't even published that yet.
Oh, I see.
Yeah. So we're still thinking about it. It's very likely that it's a topological theory. It gives you the bare minimum of what I want. But clearly, if you put it on more interesting manifolds, there could be more interesting things to say. Yeah.
Could you go back a few slides, two slides ago? Yeah, I didn't get one B was diagonal. That's the idea.
Okay, so you recall that when I did it in gauge theories, there was an F, and then there was some term involving velocities, but I diagonalized this by saying that this is some diagonal value. And then E dot ds was some diagonal entity which I called some charge associated with that. And then the U's gave me the dynamics as you see here. So if you look at this term, there should be a U here. It's not G, it should be U. And this U V U inverse is the original V which has 4 diagonalization. Okay, so by that, so the group element V that we are talking about is really what locally diagonalizes your charge density or electric field. Okay, that's what it is. Is that okay?
Yeah, can you give some references for this peripheral gravity? It's fascinating.
Oh, as I just told you, I haven't published it yet. It's something we are writing up now. But I can send you some stuff.
Yeah, that would be fantastic. Yeah.
Yeah. So it's a very simple theory, way too simple theory. If maybe use.
Oh, it's fascinating.
Yeah. Okay.
I was struck by your Hamiltonian for in terms of with the little gamma in it and the rotation fluid.
Yeah.
Just the Hamiltonian on its own,
Mm-hmm.
which you've written at the top here.
Yes.
If I pull gamma out of that and replace it by a half or something, yes, if I make that 1/2, it is the Hamiltonian essentially for a
Like a
for a matrix model, for a matrix of harmonic oscillators.
Exactly.
With
so it could very well be that a matrix model has this kind of fluid vortex interpretation.
which, I mean, this is exactly it. I mean, I don't know whether it's essential that, I mean, I would need to pull gamma out of the Hamiltonian.
Yeah, but I don't think that's such a big deal because I'm sure you can pull it out. This is essentially the Vandermonde.
That's your Vandermonde, so that
if
gives
you
you
quantize vortices,
Sorry?
if you have quantized vortices, then gamma can be pulled out and
I can pull it always as a coefficient in front of the Hamiltonian, which seems harmless.
If you want
I want it to go into the measure. I think in terms of
no, that's what I'm saying. If you want to go into the measure, it will be some determinant, Vandermonde raised to some power gamma.
Yes.
We want some integer value for gamma.
And the size of the matrix, the sum over alpha, is
the number of vortices in the car. So if you take a matrix model in large limit, it could very well be that there is a vortex fluid interpretation of that. I don't know if anyone will.
Even at a finite end, here is
even at finite end. Yes, that's correct. And I don't know if anyone has done that. No, offhand, I don't know anyone doing that. But astonishingly, this was written down by Mr. Griffith in 1880s. It was quite impressive.
This is the one with regard to currents.
Same guy.
That falls into the dimer model in terms of this interpretation of it in terms of sand piles.
Okay.
So,
okay, I don't know much about it to tell me. Yeah. But it's a kind of an interesting thing. And he noticed that these Z and Z bar, the transverse coordinates of the vortices, are Poisson conjugate to each other.
Yes.
So it's a very nice observation.
No, it's a beautiful observation.
Yeah.
That's surprising.
Yeah. So anyway.
Any other questions? Okay, let's thank Parameswaran.
Thank you.
Is there anyone online that wants to ask a question?
Okay, I will start the recording. They usually pop over. But it's just so well.